Okay, hello to everyone. First of all, good morning to the American and Canadian colleagues, and good evening to those of you that are in China and India, from what I saw, and also in Europe. I think it's now later in the day in these continents. Today's talk is going to be about the clean energy transition that is implemented day by day. I wanted first of all to thank very deeply Professor Krishna for his kind invitation and the University of Illinois at Chicago for running these seminars. I think this is an excellent opportunity for everyone to be involved and to get to know new topics. Okay, I will start by saying I think we had a small discussion with Dr. Krishna that about the emerging areas, and this is very important, and that reflects also our experience in the sense that we all started in different areas. I started from groundwater hydrology at the University of Arizona in Tucson, but scientific needs shift, and right now things change very drastically. So what one must do, must follow, okay, what happens and what are the important topics of today, and transfer the tools that we are having. Of course, we cannot move away from our tools, so we transfer the tools to different areas. So here is a topic that I think you are going to find interesting because it is really the talk of the day, as you can say. This has to do with the clean energy economy that is evolving on a global scale. So I will give a very broad overview and highlights of what is happening to convince you that this is really something that is not theoretical, that will happen the next 20 or 30 years, but it's happening as of now. And then the second part of my talk will be on the critical minerals, metals that are needed that are needed to make this transition a reality. And then, okay, in this part, I will discuss several aspects which have to do with where these minerals are found and some of the environmental issues that are related with the extraction and processing of these minerals. And I will conclude with a few concluding remarks. So some highlights on the clean energy economy. Everybody's talking about that. So here is a picture of the last climate change conference that took place in December of the past year in the United Arab Emirates, and you can see a picture of this one. And the important thing is that the decision that was reached and was signed by 146 nations was that we need to transition away from all fossil fuels and to reach net zero emission by 2050. Interestingly enough, this proposal came as a compromise and was promoted by the United Arab Emirates, which, as you know, is one of the leading gas and oil countries in the world. Okay, so based on this, ministries and governments for the last years have adjusted their priorities and their strategies. I'm giving some examples here from the United Arab Emirates. For example, the ADNOC, which stands for Abu Dhabi National Oil Company. It is one of the top 20 oil companies in the world, decided on a sustainability strategy and set specific goals. And if you read the first line that I have below, it has decided to decrease the greenhouse gas emissions by 25% in the next 5-6 years. Okay, so this is a very ambitious target. Okay, apart from ministries and corporations, universities, as you all know from the university that you are in, are following suit, okay, with sustainability groups and strategies. And here I have the screenshot from the site of the University of Illinois at Chicago that talks about the university becoming carbon neutral, okay, carbon neutral university. So clearly, something is happening both at the government level, at the corporation, and also at the university levels. So, I guess all of you are familiar with this graph, okay, which is a standard graph that shows that the 800,000 years, what has happened to the carbon dioxide. And there are two obvious observations that one can see is that, okay, the graph that relates to the carbon dioxide is very closely following, or actually the opposite, the temperature in the Antarctic is very closely following the fluctuation of the carbon dioxide. Okay, so that's very important to realize that the peaks and the lows, okay, are happening, and the lag, okay, of course, given that we are talking about a big time scale, the lag, okay, seems to be a very minor, and basically that the system reacts very quickly to CO2 increases. The other important thing to notice is that if you look at this graph, okay, the one maximum value that perhaps one can observe is around 300 parts per million, okay, approximately. And what I have on the right, I have a picture from NOAA that shows the very recent, the June 2024 measurements, okay, of CO2, which vastly exceed, as you can see from the number, what has been a historical record of almost 1 million years. So clearly there is a problem here, okay, and I think we all know about that, okay. This problem, of course, is reflected with many things that we have seen in all our countries, okay, from floods in certain areas and droughts at the same time in the, sort of desert southwest of the United States. And I have decided to put the hurricane situation here because the Hurricane Milton was a major piece of news that threatened, massive destruction for Florida. And what you can read is that basically, okay, what NOAA has detected is that the strength and duration of the hurricanes over the Atlantic and Pacific have doubled the last years. The graph on the left is also very interesting, that shows that as we are moving more and more into the warming up of the atmosphere of the planet, okay, what you can see is that the category 1, 2, and 3 hurricanes are decreasing, which is a good thing, but the bad thing is that, okay, they're decreasing, what is increasing is the very big hurricanes. And that obviously, again, I'm trying to give sort of simple explanations. This is reflected, this is a result of the fact that the sea temperatures have increased, and therefore these systems, okay, are propagated by a lot of energy. Now, this is a graph from the European Commission in 2024 that shows the different countries, the level of greenhouse gas emission from the different countries. And what stands out, of course, is the China, that is, almost emitting as much as all the rest combined. These are the 6 top countries in terms of emissions: China, United States, Brazil, India, Russia, and the European Union 27. You can see that the United States is high, but it has decreased, has reduced its emissions. And from what you can read, the United States has decreased its emissions by 4%. Russia has also reduced its emission by 13%. And the impressive accomplishments by the European Union that has decreased its greenhouse emissions by 34%. On the contrary, China has more than quadrupled its emissions in 2023 relative to the 1990. India has tripled them, and Brazil has also increased them substantially. So this is the global picture of the emissions. And now, okay, in terms of the economic sectors, okay, it's interesting to see where the emissions are coming from. And I have chosen to put the United States together with the European Union because you have pretty much the same top players in terms of emissions. And this is the industry, the electric power, first of all, the transportation, and the industry. And what you can see is that, okay, for example, United States, the industry has a 23% contribution, whereas in the European Union, this contribution is 20%. The power is 25% contribution in the greenhouse gas emissions, and whereas in the European Union is 27%, and transportation is high in both of these countries. Transportation is 28% emitter in the United States and 23% emitter in terms of European Union. Okay. Now, this is a picture of China and India, and you can see that this is different in terms of United States and the European Union. So instead of the 23 to 25% that we had in the electricity, you have numbers here that are in the 50 plus percent contribution in greenhouse emissions. The industry is at par with both the United States and the European Union to around 24, 25%. And transportation is slightly slower, as you can see. And I guess this is, again, broadly speaking, this reflected by the fact that these two countries, both China and India, are really proceeding with developing their economies very aggressively the last decades. So this is a summary of what I discussed already in the previous graphs. What happens between the two blocks, which is the United States and the European Union, what happens with China and India in terms of the greenhouse emissions. Now, a very important topic that has come up in the very last years, it has to do with hydrogen. So hydrogen is becoming the big news in terms of as an energy source. And I will walk you through some highlights, some examples of what's happening in some major countries. And this, first of all, shows the decision by the European Union to diversify after the war with Ukraine its energy resources away from Russia. And you can see that what the European Union has decided is to have 5 corridors, as they are called, energy corridors for hydrogen. 2 of these corridors are coming from the north, okay? They are from the Nordic and the Baltic Sea, and they will provide hydrogen to the northern part and some of the central part of Europe. And 3 of the corridors are from the south. Corridor B is coming from Portugal and Spain. Corridor A that will start from the North Africa, Algeria, Tunisia, will pass through Italy. And Corridor E, which I will detail a little bit more because I think it's related very much to the audience that we have, that connects India to the Gulf countries and Cyprus and Greece. And this will provide hydrogen to the eastern part of Europe. Okay, so this is, my discussion will be mostly on Corridor E. Okay, so some of the big players, and these are the big players in terms of the oil and gas, like Saudi Arabia, are very quickly the last years diversifying their economies away from the dependence on oil and gas. Okay, so here is a huge project. There is a city of Neom that will be created. This city will be the size of Belgium. So those of you that are from Europe, you can understand the magnitude of this project. And this will be the place where hydrogen will be generated from Saudi Arabia, one of the biggest places, okay? In order to generate hydrogen and split hydrogen with a different method, you need energy. So you are going to be producing energy, but at the same time, you need energy to do that, okay? And this energy is going to come from renewable sources. And so in this particular case, you are going to have wind and solar parks that will generate 4 gigawatts of energy, and this energy will be used to produce hydrogen. And this is very important, the date's very important, by the end of 2026. So this gives you a glimpse of what I said, that things are happening very fast. They are not happening in the order of decades, they are happening in the order of a few years. So Saudi Arabia is the first major player in hydrogen. The United Arab Emirates has a declared intention to capture 25% of the hydrogen market. So that's really a very big, ambitious goal that the UAE has put together. Let me explain simply some things here. The terms that are used for hydrogen is green hydrogen. This is the hydrogen that comes from water through electrolysis. And the blue hydrogen is the hydrogen that comes from methane, from natural gas. okay, with steam methane reforming process. And this blue hydrogen process is perhaps not so desirable because one of the end products is carbon dioxide, and this is followed by, therefore, okay, countries that are going through that route are also developing okay, carbon capture and storage facilities. So to come back to what Krishna was saying about the different areas, okay, not everything is about chemical engineering. For example, the carbon capture and storage is something that geotechnical people, environmental people, geologists, geochemists need to, can work on. So this is a very important topic for many, many disciplines that all of us, okay, have studied. And what the picture is showing that in the United Arab Emirates, this is a solar plant that is going to be put in operation in 2026 in Dubai. It will generate 1,800 megawatts of power, and this energy will be used to produce green hydrogen from another plant that will be created in Dubai. Interestingly enough, what the right picture is showing, this is showing the pavilion of ADNOC. ADNOC, again, is the Abu Dhabi National Oil Company. This was their pavilion in a big exhibition and conference, and was expecting them to be advertising their gas and oil operations. Instead of that, what you can see is that this major oil and gas company is advertising its involvement with hydrogen. Now, coming to India, okay, India is a major player in terms of the wind energy. So wind farms in India have moved here by 2015 in the fourth place in terms of wind power generation, behind China, USA, and Germany. You can see some of the major wind farms that exist in India. And for example, if you take the first one, Mupadal, the wind farm of Mupadal, it's equivalent of what the United Arab Emirates is planning to produce as energy from renewable energy. Okay, so I presented before the Dubai, which is 1,800 megawatts. And there's another big solar park here in Abu Dhabi, which is a SAMS solar power plant. This is about 100 megawatts. So the Mubadal wind farm alone is pretty much, okay, what is the renewable energy that is planned to be produced in here in this country. And the ambition, actually, the goal for the Ministry of New and Renewable Energy of India is very, very big, as you can see, because we are talking now that by the year 2022, the goal is to reach 60,000 megawatts of power. Okay. This is a picture of the Mubadal wind farm. Okay, this is a Google Earth picture that I took, okay, yesterday. I think you can see some of the white poles in the picture that indicate the locations of the wind turbines in this location of India. Now, okay, so we talked about Saudi Arabia, we talked about the Gulf region, okay, as a representative having the United Arab Emirates. We talked about India. Let's move now to Europe. And here what you can see, apart from what I showed in the beginning, the 5 corridors, you can see that the European Union has declared that they want to increase by 2050 their share of hydrogen from 2% that is now to a much higher percentage, to 14% by 2050. There is really a very frantic pace and activities that are going on in many countries in Europe. Okay, I'm highlighting one of the projects that is going to connect Spain and France with a hydrogen pipeline. The cost is 2.5 billion. This is something really as a small part of the whole pie. All countries, pretty much most countries in Europe, have developed a national strategy for hydrogen, and the amount of euros that are spent are in the tens of billions in each country to develop their strategy and their resources in terms of hydrogen. Now, in terms of China, this is a picture from China that the location where China is planning to develop 100 gigawatts of renewable energy, and this renewable energy is going to be used for developing hydrogen. Okay, so this is Chinese are also very active in this game of developing hydrogen. Japan is very impressive. It was the first country that was developed a national strategy for hydrogen. And their prediction is that this market will be a market of close to 2.5 trillion per year by 2050. Some impressive things that have happened in Japan is that the first vessel, which is called Suiso Frontier, was developed. This vessel can transport liquid hydrogen at temperature of minus 253 degrees and will bring back and forth hydrogen between Japan and Australia. At the same time, JR East is test driving the first hybrid train that will operate with hydrogen. It's called Hibari. And JR Central, as you can see in the picture on the right, is developing a hydrogen engine for trains. Okay, so here you're talking about a very quick pace in terms of technological developments. Now, coming back to United States, okay, this is ExxonMobil, the site of ExxonMobil that also advertises hydrogen. And at the bottom part, you can see that in Baytown, Texas, there is going to be a blue hydrogen plant that will be created. This is going to be from methane. Okay, so they will utilize methane to break methane and capture hydrogen. At the same time, they have also found locations, geologic formations where they're going to be doing their CO2 storage. And this plant in Texas will generate up to 1 billion cubic feet of hydrogen per day. So this is really a massive investment that ExxonMobil is doing in terms of hydrogen. So this is sort of a very broad overview, I think, to convince you that, everybody's in the game of hydrogen in every country. It's a very big game that is changing the geopolitical structure of the world. And, all the major players are really in a race of who is going to really start first and, capture part of the market as soon as possible. So now let's move now to the second part of my talk, which relates to the metals that are needed for this clean energy economy to be realized. And here is the International Energy Agency that has identified 5 minerals that will be very critical. These will be the 5 minerals that will be critical in developing this clean energy technology. And these minerals are copper, a traditional metal, cobalt, nickel, and the two ones that are in the list, lithium and rare earth elements. Rare earth elements is not one, it's actually a family of 17 elements. Lithium and rare earth elements I'm sort of separating from the other two because these have been, their properties have been fairly recently been investigated as energy storage material. And therefore, the issue here that I'm raising is that, okay, we have very few mines of lithium and rare earth elements. Therefore, the supply is not going to be at par with the demand. Rare earth elements are called like that, not because they are rare. They can be found easily on most parts of the world, but the quantities that they are found are very small, and therefore it's not economically feasible to extract them and process them, okay, to process rare earth elements. Okay, the same thing from International Energy Agency. You can see the picture from the USGS. report, Minerals Commodity Summaries, and USGS identified 50 metals that are of strategic importance for the economy of the United States. And these metals of copper, lithium, rare earth elements, cobalt, and nickel are also featured prominently in that list. Okay, so this is the USGS report. And at the same time, what you're seeing on the right, you are seeing the European Commission, the latest report, which is of 2020, which is the report on critical raw materials resilience. This is the report by the European Union. And in this report, the European Union was trying to identify the countries and the locations where some of these metals are found. And you can see the picture here that, you have an uneven distribution of metals that are sort of, very prominently segregated in the eastern part of Europe, okay? And you have very few locations in the central part, okay? France and Italy, for example. Okay? Now, what are these metals, where they are used? Okay, so you have, okay, the wind turbine and the photovoltaic panel, and you can see the list of the metals that these technologies are utilizing. And I have highlighted here with blue these metals that are in the list of the critical metals. So copper, nickel, and neodymium, okay, in the wind turbines, and copper and nickel in the photovoltaic, okay, together with other metals that you see that are required, okay. Of course, the big elephant in the room is, as they say, is the energy storage, okay, and you are talking about the batteries. The top picture shows the common batteries that you are using in everyday life. And you can see some of the metals that go into these batteries. And prominently, again, you have lithium here. Okay, you all know, we are all familiar with the lithium batteries. And at the bottom, I'm showing a picture of a Tesla battery car. Okay, and this is actually one of the problems that we are having with the metals. And we'll discuss it in more detail in the next slides, that a typical battery of our conventional car that we are all perhaps using until now is having a weight between 11 to 23 kilograms. Okay? The typical Tesla battery has almost 7,000 individual lithium-ion cells and will weigh up to 400 kilograms. Okay, and this is more of a medium Tesla car, okay, where the bigger models can reach even almost close to 1 kilogram of a battery. Okay, so bottom line, and this is a picture now again from the International Energy Agency, electric cars need many, many more metals than conventional cars. And you can see that on the top screen, where it compares electric cars versus conventional cars. You can see, okay, now we're going to see in more detail in the next slide, the copper needs, the lithium needs, etc. But the same thing applies also to the energy sources, because at the bottom, if you look at the bottom graph, okay, you can see the coal and natural gas at the bottom part of the graph, and you can see the wind farms offshore and onshore on the top, and the solar photovoltaic in the top. And you can clearly see that the metals, again, in kilograms per megawatts power, okay, is much higher than what we are actually utilizing up to now. This is a detail of the conventional versus electric car type of comparison, and you can see the quantity of copper at the bottom of a conventional car that is almost doubled or even more in the electric car. The manganese, which is common to both, is again doubled in the electric car. And now you start having some metals like lithium, manganese, and cobalt that some of them, like lithium and cobalt, are critical for other technologies as well. And you can see that now they appear in the electric car. So clearly the picture shows that the amount of minerals that we will need to make this transition to the clean energy economy is going to be much higher than what we are used up to now. It's not only the electric cars. This is the picture of our smartphone, the different parts of our smartphone and the metals that each part is utilizing. I'm not going to go into details into this. I think you can see them, and later, if you download the recorded lecture, you can read some of these more details. I have highlighted with blue these minerals that are belonging to the rare earth category. Okay, so these are what some of these are going into our smartphones. Now, so I think we saw the quantities that are required. Now, what the International Energy Agency is saying is that basically the demand for rare earth elements is expected to be multiple times by 2040 of what we are having today. Lithium may even be even worse, even a 40 times demand in 16 years from now. Okay, but even some of the metals that we are familiar with and in everyday life, like copper, because of the high demand that copper is having from these new technologies. Okay, so there is some projections, and you can see that. Okay, there are some projections that may be a deficit in copper by 2023, and that will last until 2030. Okay, this is another picture that shows how the demand in lithium in thousands metric tons has evolved from 2020 and what is the projected demand by 2035. And clearly you can see that the numbers are staggering from 310,000 metric tons that were used in 2020. We will be needing, 10 times or 13 times, 14 times more in pretty much, in another decade. So the quantities of lithium that we will be requiring will be staggering. Okay, the same story applies to the rare earth elements that are expected to almost triple in terms of the demand by 2035. And this is actually now a good point, to discuss something in the second bullet. It says that in order to meet this demand, the governments need to spend at least $30 billion between 2022 and 2035. And here, what I wanted to remind everyone is that mining, from the time that some resource is identified until the mine is put in actual production, it takes several years. In many cases, it may take 10 to 15 years. And in some cases, in countries where the infrastructure is rather poor, for example, you don't have the roads or you don't have the labor and all that, this can even be expanded even longer. So clearly, finding new mines is one task, but being able for these mines to be able to produce the needed quantities for the economy is a completely separate and very difficult issue. This graph shows, in percentages, compares 2018 production levels versus 2050. What will be the needs by 2050 in percentage-wise, So graphite, lithium, and cobalt, as you can see, the demand from 2018 to 2050 is expected to reach over 450%. Okay, so this is a very, very big number, as you understand. Cobalt, the other on the 200%. So clearly, there are from multiple sources you can see that we are dealing with vast quantities of metals. And obviously, this non-equilibrium between supply and demand creates problems with the price of these materials. And here is a picture from the fluctuation in the price of lithium from 2020 to 2024, where a big fluctuation can be seen, okay, over the years. Countries are, really struggling to develop new mines, and what I'm showing here is a, very big mine of rare earths in California and United States, the Mountain Pass mine. You can see a picture of Google Earth picture here. And there are these talks, as you can see from the article from Bloomberg, that the United States must develop actions in order to access some of the critical minerals that are found in Africa. Okay, so this is sort of a broad introduction on the critical minerals. Let's move now to see some of the details about where these minerals are found and some of the issues that relate to their location. So this is from the International Renewable Energy Agency. So cobalt, at 70% of the cobalt resources, the non-cobalt resources, are the Democratic Republic of Congo. Dysprosium is found almost 50% in China. And if you add up Myanmar and Australia, these three countries capture 80%, okay, of the dysprosium reserves. Manganese, South Africa has about 36% of the resources, and Gabon and Australia has another combined 36%. So again, these three countries will adapt about 72-73% of the resources. Nickel is found about 49% in Indonesia and about 10% in Philippines. So 60% of the nickel is found in these two countries. Okay, let's move on to see copper. Chile and Peru are traditional powers in copper. Okay, and the Democratic Republic of Congo is also appearing in the copper production. Iridium, which you saw it used in the smartphones. South Africa has 90% of the iridium, and with Zimbabwe, you are reaching a number that's close to 90%. Lithium is 46% in Australia, 30% in Chile, and 14% in China. So basically, almost 90% of the reserves are found in these three countries. And, I will let you look at the other, okay, and I will not, go into the next of details. So, okay, this is a picture of the lithium mount, okay, which is from a lithium mine in Chile, okay. So, what is some of the conclusions from the previous picture that I showed? That the critical minerals are highly concentrated in very specific geographic locations. Okay, so Australia has a dominance in lithium, Chile in copper and lithium, etc., etc. And as I presented before, 2 or 3 countries may be capturing 80 or 90% of the resources of a certain metal. Another interesting observation may be that, okay, although the Western societies or countries have the know-how and the technologies, you saw that the United States and the European countries are pretty much absent from this list. And therefore, they have the know-how and the technologies, but the resources are found in Africa and Latin America and other Australia, okay, and South Africa, okay. Processing now, it's not only a matter of the resources, okay, because resources may not mean that there is actual processing taking place. Processing is even more concentrating, with China having a very big role in the supply of graphite, rare earth elements, lithium, cobalt, and manganese, that creates problems of monopolies, okay, global monopolies. And the trade of this material has reached is reaching a point where really, okay, no country can isolate itself from the fluctuation or supply disruptions that are happening at the global level. There are some structural issues that have to do with decline in the ore grades, meaning, okay, you don't get to find, okay, rich ore grades. There are geopolitical risks. You saw the list of the countries, and now you know these countries, some of them are not very stable politically. There are situations like what happened, for example, with some resources in Tanzania that you may have some of these industries being nationalized. There may be bans in exporting some of these minerals, and you may have situations where cartels and market manipulation may take place. And clearly, okay, because everybody is rushing to in this game, okay, you can have geopolitical competition for reserves that are found in some location. I will go rather quickly because I think I need to give some time. So what some of the environmental concerns that, okay, first of all, that water needs. Mining, okay, is very water consuming. For example, okay, 1 ton of mine, 1 ton of lithium requires from, depending on the situation, you can see the numbers, tremendous quantities of water. And now if, okay, you are going to translate in terms of the EU and taking an average of 200 liters per day consumption per capita, which is really a high number because in the European Union, the highest consumption is in Italy with 238 and Malta has a consumption of 50 liters per day. This quantity of water to extract 1 ton of lithium corresponds to, you can see on the average, around 7,000 people, the water for 7,000 people daily. So clearly, there is competition for water, okay, from the new mines. And this is a picture from the World Social Institute that shows the water-stressed region. And interestingly enough, this report, okay, I have put together the correspondence of the water-stressed regions and where these critical minerals are found. So, for example, South Africa, which is really a very top country in a lot of these minerals, is in the category of extremely high water stress. Okay? The Chile, which is one of the top countries in copper and the second in lithium, is found in the extremely high, okay, also over 80% water stressed area. Peru is in the high, 40 to 80% stressed, and it's second in the copper reserve. In Australia, which has an abundance of resources, is in the medium high. So the conclusion from this is basically that unfortunately minerals are found in locations where water is scarce and mining requires huge quantities of water for processing. Now, okay, what happens? Okay, so this is a picture of a mine, okay, in Chile, okay. Okay, very quickly, what I want to mention is that all the processes that are involved in mining, okay, some metals require, first of all, water, okay, flotation, okay, for, to separate some of the material, and then the use of chemicals, again, to separate the desired metal from other impurities that may exist. What is left is called tailings, and I think you had a very interesting webinar that this was discussed in more detail, waste tailings, which is a liquid mass that has the water that is now discharged together with some of the chemicals that were used in the processing, together with some of the impurities. These are put in evaporation ponds, okay, for the water to evaporate, and these evaporation ponds are held at the front by a dam. Okay, these are the tailings dam. This is a picture of the San Pedro in Chile evaporation pond. You can see some very nice colors here, and these colors are the result of the different pH that you are having in these different ponds. Okay, the tailings dams are huge, both in height and the extent, okay, in order to hold this material behind them. And now this is a picture of the San Marco, okay, copper mine in Brazil, and a very significant accident took place in 2015, November 5, 2015, where the dam that was keeping the waste pond material behind collapsed, and now 33 million cubic meters of mine waste were discharged into the Doce River, which is the fifth largest river river basin in Brazil. It traveled for 65 kilometers, clearly polluting, okay, sediments and water in all this path, and discharged 17 days later in the Atlantic Ocean. And this is a picture of, of a December picture, satellite picture in December of the discharge of this river to the Atlantic Ocean. And on the right, you are seeing a picture that is fairly recent of the past year, that the situation has improved, but clearly, okay, you still have the repercussions of this vast pollution event. Okay, I will finish very quickly. Okay, so mines, okay, of course, need to be developed, but mines create big environmental problems. So clearly, okay, mine operations have to be vastly improved. The other issue that we're having, it has to do with recycling. There is very little recycling of electrical and electronic equipment that is taking place. This is a picture of the European Union that is pretty much better shape than others. You can see the colors represent the years. You can see the electrical and electronic equipment that are put in the market from 2012 to 2021. And you can see what was collected, which was a much smaller fraction of what was put in the market and what was recovered and recycled. Okay, in other countries, okay, for example, in the United Arab Emirates, you can see that there are campaigns to recycle some of them smartphones. So up to 2019, okay, one of these campaigns collected almost 60,000 mobile phones, which sounds like a good thing, but if you look at the bottom, okay, in this country of 10 million people, okay, there were 7 million smartphones that were sold in 2022. So clearly this is just a drop. The recycling that is taking place was just a very, very small part of what is put in the market. And the last thing is that, okay, recycling is not problem-free. This is an area in China where 6 villages are specialized, the population specialized in disassembling and retrieving some of the material from laptops and smartphones, etc. And studies that were done of dust, soil, river sediment, and groundwater found heavy metal pollution and toxic heavy metals, organic contaminants, and actually the cancer rate in this region increased significantly after they got into the business of recycling, okay, electronic equipment. So in conclusion, okay, the transition to the clean energy economy is taking place today. It is a thing that is happening extremely fast. It may not make the big news, but if you sort of follow some of the smaller things, you are going to see the head of the states that are meeting with each other to discuss their strategies. On the other hand, the challenge is that the critical minerals that are needed are not there in terms of the quantity. So the demand is expected to vastly outpace the supply. This requires, first of all, new mines, clearly, that will also develop new technologies and processing that will not harm the environment. And at the same time, we need to rethink about and put in action the recycling and reuse of electrical and electronic equipment. Thank you very much. I wanted to leave you with this very nice picture of the Yellowstone Park, where nature is pure and pristine because it's preserved. Okay, and I will be open to questions.